Welcome, geometry students, to Unit 11.2, Area of Regular Polygons. This is Mr. May. Let's begin. Our learning targets. Learning target number 1, I can find the perimeter of regular polygons. Learning target number 2, I can find the area of regular polygons. Looking at the two learning targets, a couple of similar vocabulary words. Let's first cover regular polygons. So we have regular polygons with a connotation that is very specific to geometry. Regular referring to equilateral or congruent sides, and equiangular meaning congruent angles. So we have congruent sides and congruent angles of a polygon. And once again, we're going to have specific polygons we're working with. We learned the specific names of them in the prior unit. So with these regular polygons, we're going to find both the perimeter and the area. Our definitions: the center of a polygon is the point on the interior of the polygon that is equidistant. Here's that vocabulary word again, equidistant. If I were to break it down, we have meaning equal, distant, which seems to be self-explanatory, but equal distance from each vertex. And so whenever we have that point on the interior that is the equal distance from each vertex, we have found the center of that polygon. Also notice that it would be the center of the circumscribed circle. So on this particular polygon, we have a circle that circumscribes. Again, circumscribed refers to the fact that it is touching all of the vertices of the polygon. In this case, we have a pentagon. And the center of this polygon, which is O, is also the center of that circle. Now, when I say we're equidistant from all the vertices, that means that this particular point is equidistant from all of these vertices. And so all of these multicolored lines are the same length. And I can't say lines, I need to say segments in order to keep my terminology correct. And so we have point O is the center of the circle and the center of the regular pentagon. That is what is being referred to in the second point when we specifically discuss the circumscribed circle about the polygon. For it to be circumscribed, remember it has to intersect all of the vertices. All the vertices must be on the circle for it to be a circumscribed, for the circle to be circumscribed about the polygon, and they share the same center. The radius of a polygon is the distance from the center of the polygon to any vertex of the regular polygon. This radius is also going to be the radius of the circumscribed circle. And so when I look at this particular diagram, notice that they have the center of the both circle, and in this case we have 1, 2, 3, 4, 5, 6. We have a hexagon, but it is a regular hexagon. So we have the center of the hexagon, we have the center of the circumscribed circle, and if I were to draw a radius of this particular polygon or hexagon, it must go to the vertex. Okay, now I could draw multiple radii, I could draw to this vertex, I could draw a radii to this vertex, I could draw a radii to this vertex. Those are all radii of the hexagon. However, there are also radii of the circumscribed circle. One thing that we need to distinguish is that there are more radii of the circle than radii of the polygon. I could draw a radii to the circle here, but it is not a radius of the polygon because it does not go to a vertex. And so all of the blue radii are radii of both the circle and the polygon. The red is only a radius of the circle. And so there needs to be a distinction between the two. The apothem of a polygon is a line segment. Once again, we have a segment, meaning that it has endpoints, and it's drawn from the center. So I must locate the center. And it is drawn perpendicular. Okay, so it's drawn from the center to form a perpendicular bisector. And so perpendicular, when we look at this vocabulary word, perpendicular, we know that it forms a specific type of angle, and that angle is here, and we know that that angle represents a right angle or a 90-degree angle. So we are forming a 90-degree angle, but not only that, it is a bisector of the side. So if it's a bisector of the side, if this is my total side, then I know that a bisector divides that side into two equal parts. And so this side, the blue side, is going to be equal to the pink side. So if I add the blue and the pink together, I would get the total, which is the green. And I know that the blue and the pink are equal to each other, and that the segment that is bisecting that particular side forms a right angle with the segment from the center. So we have a perpendicular bisector of the side. If I did have just to show you an example, going back one, if I have a circumscribed circle about the polygon and I want to draw an apothem, one thing that you need to be careful, this apothem stops at the polygon, okay? It does not go all the way through to touch or to end on the circle. It stops at the polygon, so it forms a right angle with the polygon, and then we know that it is a bisector of that side, meaning that each of those two segments will be equal. The central angle of a polygon is the angle formed at the center of the polygon by line segments drawn to two consecutive vertices. Well, consecutive refers to next to each other. And so here's our consecutive vertices. We have two line segments. So here's our two segments that are drawn to each of those. And then our central angle is this angle that is formed by those two segments. Now, if I want to find the measure of that central angle, what I would do is I would take 360, and this is true for all polygons that are regular polygons. I take 360 and I divide it. Let's actually write this down here so you can. So the central angle measure is equal to 360 divided by n. And once again, we always call n references the number of sides. So if it were a 10-sided figure, we would have 360 divided by n. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8 sides. So we have 360 divided by 8 in this particular example. So we would have 360 divided by 8, which is equal to 45 degrees. So the measure of the central angle, 2, 3, 4, 5, 6, 7, 8, and this measure of this central angle would be 45 degrees. Our theorem, or our first theorem, is that an area of the equilateral triangle, again, an equilateral triangle means that we have equal sides, but it also means that we have equal angles. It's also equiangular. But we know that there is a specific formula for an equilateral triangle calculated as the area is equal to 1/4 the side squared times the square root of 3. This is a formula. Now, an important point that I want to make here is that anytime we're working with a formula, formulas are referenced by capital letters. Okay, so I have a capital A, which means that I am working with area. It's a formula. On the other hand, if I have a variable, which in this case, this is the side and it is a variable, this is a lowercase letter. So I have a lowercase letter when I'm working with a variable. And so what I would do if I had an equilateral triangle is if I want to calculate the area, if I have an equilateral triangle, then I would know that all my sides would be the same length. And so all I would do is I would take the length of one side, and so in this case the length is 10. I would substitute it in for S, and I would calculate that using most likely a calculator. And so what I would end up with in this particular case is the area is equal to 1/4 10 squared times the square root of 3. Entering that into a calculator would give you the area of an equilateral triangle with side lengths of 10. The area, another theorem, the area of a regular polygon. Once again, regular has a specific meaning in geometry, equilateral and equiangular. So the area of a regular polygon with side lengths S, once again our side lengths S, it is lowercase, okay? So it is lowercase because it is a variable, is 1/2 the product, okay? Product meaning multiply, so we're going to multiply product of the apothem, which we just learned as a vocabulary word. So the apothem A and the apothem A, okay, and the perimeter P. Now there are some interesting things that we need to discuss here, and actually I want to use a different color because I've already used that. Let's go with this, P. Okay, so there are a couple things that we need to discuss. First of all, what I have found in prior years that this double equal sign really throws students for a loop, okay? Now, what this is just saying is that the area can be calculated in one of two ways. So think of it as dividing this into two pieces, okay? I'm going to take this and I'm going to divide this right here. So I have two options. Option number one, I can calculate the area is equal to 1/2 A the apothem times the perimeter. Option number two, I could calculate the area is equal 1/2 the apothem times the number of sides times the side length, okay? So those are my two options, okay? And what this is actually showing right here, this is showing the combination of both of those, okay? It's just writing it in sequence, okay? It's not dividing it out. So that's the first thing I wanted to discuss. The second thing I want to discuss is notice that I've got two capital letters. Remember, capital letters refer to formulas. So this is referring to the formula for area. This is referring to the formula for perimeter. Okay? It's a capital letter. So if I want to use option number 1, I have to calculate the perimeter first, okay? I must calculate perimeter, okay? Whatever I get for the perimeter, I am going to include in my formula for area, okay? So that is a formula within a formula for area. So if I use option number 1 for area, here's option number 1, is the area of a regular polygon is equal to 1/2. That 1/2 is a constant, okay? It's always going to be 1/2. The length of the apothem, okay? So this lowercase a, it's lowercase, it's a variable. It's going to be the length of the apothem. Remember, apothem is a new vocabulary word. I'm going to go back here. Apothem, again, here's our apothem right here. Forms a right angle and it is a bisector of the side, okay? So there's our apothem. We would take that length, okay? That length we substitute into our formula for area here and then multiply it by the total perimeter. That is option 1. Option 2 for area, down here, option 2, to calculate the area, we still have the same constant 1/2. It's the same 1/2. We have the same variable for the apothem. Now what is different is that we have n times s. Now all this n times s is it's basically the deconstructed formula of the perimeter. So this is the actual formula for the perimeter of a regular polygon. Okay? And so what that formula says is n, we now know, is the number of sides. And we know that s is the side length. And so basically you're taking the number of sides and multiplying them by how long they are. So if I had a square, for example, okay, and I know that all sides are going to be the same, I have two options to find the perimeter. The perimeter is equal to 5 plus 5 plus 5 plus 5, which is 20, or because it is a regular polygon, all the sides are the same length, I know that I have 4 sides. I could multiply it by the side lengths, and I would get the same 20, okay? Now, if I use this method, basically what I am doing with this method is I am using formula 1, and if I am using this method, I am using option number 2. Either one is going to give you the same result. It's just a matter of preference as to which one you want to use. Just realize these two formulas are calculating the exact same thing, the area of a regular polygon. You can use option 1 or you can use option 2. The only difference is how you calculate the perimeter. And so with that, this concludes Unit 11.2. As always, if you have any questions, I encourage you to go back and re-watch portions of this instructional video, work some of the examples, create some examples of your own. If you have questions beyond that, please ask one of the math teachers. We are more than happy to help you. And as always, I hope that you have a great day, and we do look forward to seeing you